So the second talk in this session is going to be about type subtraction, and it's going to be presented by Xuejing.
Okay, mic work. Okay, so let's get started. I'm Xuejing. Today I'm going to talk about making a type difference subtraction on intersection types as generalized record operations. This is a joint work with Xuejing, Huang, and Bruno, Oliveira. To get started, we first need some background knowledge of intersection types. And here a small example using an intersection type. This example program uses a variable x of the intersection type int and bool. The x here will be passed to the tuple successor x and not x. Successor x requires x to be of type int, while not x requires x to be of type bool. Because the x has intersection type int and bool, so it can be typed as either int and bool. So this program will pass the type check and compile successfully. Actually, intersection type, along with its subtyping system, is introduced very early into the programming language. A subtyping system that is widely used for intersection types is the BCD subtyping system. Besides the commonly used subtyping rule, A and B will be a subtype of A and a subtype of B. The BCD subtyping system allows you to use two functions of the type A to B and A to C as a function of the type A to B and C. And all works are working on the basis of BCD subtyping system extended with Recor types. Now we learn a little about subtyping relations for intersection types. Next, I'm going to talk about some terms of intersection types. In 2014, Dunfield developed Reynolds merge operators into a calculus with merge operator. Merge operator, denoted by double comma here, can merge arbitrary two terms together. Here, you merge 1 with 2 together to get a term of the type int and bool. If 1 is merged with 2 is passed to the x at the program here, it will finally get a result of 2 false. One thing I need to note here is that this construction is non-classical, because in classical type theory, int and bool will be a type of empty. But still, you can use merge operator to construct terms of the type int and bool. And another thing I need to add here is that Dunfield's calculus is not deterministic, because 1 merged with 2 can be evaluated to either 1 or 2. So in 2016, Oliveira proposed the disjoint intersection type where only terms of disjoint types can be merged. Disjoint means that here the common supertype of two types can only be top. This disjoint restriction will help us eliminate ambiguity and make the calculus deterministic. Such as, we know that the common supertype of int and bool is top, and that means 1 and 2 have no common component, and so that you can always determine whether 1 merged with 2 should be evaluated to 1 or it should be evaluated to 2 according to the evaluation context. However, we cannot merge false with true because they have exactly the same type, and we cannot tell them from each other in the type context. Although the disjoint restriction enforces the determinism of the calculus, the disjoint restriction is actually inconvenient because it rules out all of the conflicting merges. So what we need is a method that can resolve conflicts and overlappings in arbitrary two terms or types, and that is what we need, the type difference. So where does this type difference come from? Actually, we can first take a look at well-studied subcases of resolving merge conflict, that is the record calculus. Record calculus provides you many operators to manipulate labels and contents inside it, and there are concatenation and extension operators for you to extend the record. The concatenation and extension operators here is restricted because you cannot extend a record with conflicting labels. So you have the restriction operators for you to resolve these conflicts. Restriction operator here, denoted by remove y, can remove the y component inside the left multi-field record. But actually, it is very similar to the merge in the disjoint intersection type because we can also merge two single-field records into multi-field records. The merge operator here is the concatenation operators inside the record categories, except that the merge operators applies to more types such as our function types. So what we want to do is to generalize the restriction operators to all kinds of types to resolve the conflicting merge between E1 merged with E2. And what we want is to generalize the subtraction A minus L to A minus B and to get a general type subtraction. Of course, we are not the first one to do it, and there have been some works done on it. And there are mainly two branches of works. Although they are not focused on the type difference, their approach can be used to calculate type difference. The first branch of work is, of course, the record calculus. The record calculus has been studied for more than 30 years, and it provides many operators for use to manipulate records. And in this case, what we want, the type difference, is the restriction operator itself. The other branch of work is the semantic subtyping. Semantic subtyping interprets types as sets. We note that on set we have many operations such as union, intersection, and negation. So semantic subtyping enables us to perform the same operations on types just as on sets. In this case, type difference we want, the A minus B can be encoded as set difference A minus B or encoded as A and negation B. But these two branches of works are not aiming at solving the problem of type difference. So these works have some limitations. As for record calculus, however, it only performs subtractions on labels and offers no subtractions for other types, such as on function types. So it will encounter some problem in this example. Here is an example that we are overloading a function. Here we want to subtract a single field record by another single field record. These two records have the same label but a different component. But because the record calculus offers no support for subtractions for functions, so it will result in an undefined behavior. As for semantic subtyping, the situation becomes more interesting. Interpreting types as sets do not have a restriction on types you want to interpret, but still, set difference is different from the type difference. And here is an example. Here, you want to subtract a multi-field record by a single-field record. Because the multi-field record is a subtype of the single-field record, so in set interpretation, it will be interpreted as a subset minus by its superset, which equals to empty side in set theory. And in semantic subtyping interpretation, the empty side is equivalent to the contradiction or the bottom type in the type. But what we want is only to remove the L component inside this multi-field record and remain the R component. And that's why this both branch of work doesn't work on our type difference. So what we will do, we will propose a meta-theory for the type difference that generalizes the record restriction operators. We will show the type difference we want to propose has very good mathematical properties, and we will provide an algorithm to calculate it. Besides the theory, we will also propose a language that carries out type difference. The language is practical itself, but again, we will show the expressibility and the correctness of our generalization by encoding all the record operators in the record categories. And after that, we will provide top proof for all the properties for the type difference and the language. And we will also provide an implementation of the language fi- based on elaboration of into a low-level language. And that is all about our work. And the first thing to ask about our work is what is type difference? Actually, we don't know it, but we can guess some property of it. What is needed for the subtraction A minus B? The first thing must be that A minus B will be smaller than A, or we can say A minus B will be a supertype of A, or we can say A minus, if A is a record, B is a record, then the record A minus B should only consist of components that are coming from the record A. And the second requirement is that A minus B should be compatible with B. or we can understand it as if A is a record, B is a record, then the record A minus B should have no common component with the record B, or we say their common supertype is top. It is denoted by A minus B star B. And the third requirement is that if we use B to subtract A, then adding back B should be able to get back A, which is A minus B, and B should be a subtype of A. And that is the third requirement we proposed. Or we can write it in a more formal notation, that is the type difference specification. And we are getting close to our final result, but this specification isn't, because it is not algorithmic and it is not deterministic. It's not algorithmic because we don't know how to calculate C just by the three relations here. Also, it is not deterministic because it will result in a family of type C instead of a deterministic C. So the question rests here is to construct and compute C from this specification. And actually, the solution is very concise. Here is the type difference we want to propose. It only consists of a set of three inductive rules: TD disjoint, TD subtype, and TD BCD. And let's take a closer look at each one of them. The first one, TD disjoint, says that if A is disjoint with B, then subtracting B should have no effect on A. Or we can take an example. If A is a record, B is a record, and they have no common components, then subtracting B should have no effect on A. And the second rule is the case that B is a subtype of A, then A minus B should equals to top. Here I use A top to denote a top type of shape A. We need a top type of shape A because the first two rules, TD disjoint and TD subtype, may overlap with each other. To make sure the type difference is deterministic, we need to change the shape of the top type. And let's take an example. Here we use a multi-field record to subtract a single-field record. Because the multi-field record has more components than the single-field record, so subtracting should remove all the components inside the single-field record, which will be the L top. L top is a top type of the single-field record. It is equivalent to the top in the BCD subtyping system. And the last rule is the TD BCD, which is the case that B is neither disjoint nor a subtype of A. Here, it can be understood as an intersection type, which intersection component is A1 and A2. In this case, we will use B to subtract A1 and A2 respectively. And after that, we will compose the result according to the shape of type A to get the final C. And let's take an example. Here, we use a single-field record to subtract a multi-field record. Because the multi-field record can be viewed as two single-field records merged together, so its intersection component will be L int arbor. L int minus L int equals to L top, arbor minus L int equals to arbor. After subtraction, we'll compose the result according to the shape of type A, which is a multi-field record, to get the final result, which is L top arbor. It is equivalent to the type arbor in the BCD subtyping system. And that is the type difference we want to propose. And here is the property of it. Of course, the type difference we propose is deterministic, that A minus B should yield at most one C. And most importantly is that the sumness and the completeness. That is, we can find a C that is satisfying the three conditions we just proposed if and only if there is a C0, that A minus B equals to C0, and C is equivalent to C0 in terms of subtyping relations. And that is the main theoretical result of our paper. Besides the theoretical result, we also propose a language to carry out the type difference, and we will show the expressibility of it, and let's see how we do it. The first thing to do is that the language is equipped with polymorphism, so type difference is also needed to extend it with polymorphism. In the case of polymorphism, the definition of top type and disjoint will change slightly, so we made another version of type difference. But we can still get the same result. It is technically the same, so I will not repeat here again. But with this new type difference, we can finally propose our language A5 minus with the two new features, E minus A and E1 minus E2. E minus A means removing all the type A components of the expression E, while E1 minus E2 means removing all the overlapping components of E1 and E2. Here is the syntax of the whole language with the new feature colored in gray. And let's take some representative examples of how to encode record operators by the new feature. The first one is to remove a label, which will be encoded as E minus L bottom, means removing all the L components inside the expression E. And the second one is to rename the label, which will be encoded as we first remove the L1 component, then we add it back in the name of L2 by the merge operator. And the last one is the record overriding, which will be encoded as E1 minus E2 merged with E2. So that is all about our work, and let's take a short conclusion. So what we have done, we propose a type difference that generalizes the record restriction operators. It has very good mathematical properties, and it is algorithmic and deterministic. Besides, we made a language to carry out the type difference. It has very good expressibility, and it can encode all the record operators in the record calculus. And all of the results are verified in code-proof assistant. And an implementation for the language FI- is provided on the website plground.org, and you can have a check. And in future, we will try to study type difference on more types, such as on union types. And thank you for your attention.
All right, so we've got plenty of time for questions.
Greg Morrison, Bruno. What happens if you change the subtraction rule for something that's meaningless, like you have a record with a label L, and you try to subtract a label Q that's not in the record? Instead of just leaving that as the original type, what if you say that's undefined? How does that change, or is it possible to work that out?
It is hard, but in our work, subtracting a label that isn't present in the records will have no effect. And I think my intuition is that it isn't compatible with the line of our framework, but I'm not sure about this.
Okay, so I have a question, which is if you go back to the syntax for the polymorphic, there we go, that's fine. Okay, so the bound that you're putting on polymorphic types in the for all type, that's alpha star A. So could you say a bit about why that particular choice for the constraints that you're putting on generic types?
Yes. If you can instantiate it by the records, for example, for all alpha disjoint with L button, and it means a type that has no L labels in present.
Okay, and so that means that on generic types, subtraction's a partial operation that depends on that bound that you put there.
Sorry, I didn't understand.
I need to tell myself to shut up again. All right, are there any more questions? Okay, I think we should thank the speaker.